only covered one surface out of 6. So we're going to work on the second one. So which second surface are we going to evaluate? We have this one, this one, this one, the one on the bottom, and the one on the back. For immediate application, we want to evaluate the surface on the back, the negative x direction. Okay? So now let's switch to the back surface. Again, we are trying to evaluate the outward flux. So for the back surface, its direction is also pointing out from the structure. So now the surface is pointing in the negative x direction, but its area is still determined by delta y and delta z. Right? So now this ds, differential surface, is having a negative sign. And its position is now offset in a negative direction as well. So it is situated at x0 minus delta x divided by 2. So this makes my evaluation for the flow on surface number 2 as ax. But now the x value is x0 minus delta x divided by 2, y0, z0, and multiplied by, again, ds, a surface in vector calculus, is itself a vector. So you have to note this negative sign. Right? This we know how to do already from the previous slide. We use Taylor's expansion to the first order. Because you have a negative sign, so we have a negative sign. Okay? So this multiplied by this, the surface is also having a negative sign. So the differential part is now having a positive sign. But this is having a negative sign. So I'm not going to work for the other 4 surfaces, but the question is, when I evaluate the front surface, I have a positive first contribution and a positive first contribution. For the back side, the first contribution has a reversed sign, right? But not the second part. So when I add the netward outward flow, only for these 2 sides, the first contribution cancels out, but the second contribution doubles. Okay? So when I add the flow on the front surface plus the back surface, I see what's remaining is the partial differentiation of the ax component with respect to x, but being evaluated at the center point of my cube and multiplied by the differential value. Right? I can repeat the process for the other 4 surfaces, but in the end, as you can see by the same analogy, whenever you do 2 surfaces, you have the partial differentiation for that given component to that given unit vector, evaluated at the center and multiplied by the differential value. So together, altogether, all 6 surfaces would give you x component having partial derivative to x plus a y component partial derivative in y plus az to del z. They are all evaluated at the center point of your cube and together multiplied by the differential value. Okay. So this is our very first evaluation to the net outward flux of the field on all surfaces. So now you plug this into here, you'll be very happy because delta V is divided by delta V. Okay, it's gone. So for Cartesian coordinate, divergence formula is extremely easy. Each component is having its partial derivative in that corresponding direction. AX del X, AY del Y, plus AZ del Z. That's divergence of A in the Cartesian coordinate system. Extremely easy, but instead of just telling you the direct result, I'm working according to the definition for you for two surfaces, and I'm showing you the process flow in hoping that you can easily try other coordinate systems on your own. So once you can properly formulate it on your own, you don't need to rely on your memories. Memories are really short-termed. Okay? But of course, if you really need the help, our TAs are very superb. They will be willing to arrange for some special teaching hour online. I don't want you to meet the TA face-to-face. Okay? Now, generalized divergence formula. Take a look, take a good look, and think about the differential length, differential surface, and differential value that I spent so much time on Monday. Divergence of A, by definition, is trying to evaluate the total net outward flux over a small value, right? So this is the point where you really have to relate and link to what I covered on Monday, differential surface. If your unit vector is an angle, then the differential length will be an arc, right? So in that case, for this example, this h1 times h3, why is it there? When you try to evaluate the flow for your second field component, you have your surface pointing in the second unit vector direction, right? Since your field or surface is pointing in the second direction, its area, its magnitude must be determined by the differential length in the first and the third directions, right? It all makes sense. So why do I want to divide by h1, h2, h3? This takes into account of unit value, right? So try to link this to what I covered. Cartesian coordinate, differential length, dx, dy, dz. Cylindrical coordinate, the differential length, dr. In the phi direction, because phi is an angle, so you need to take the arc radius into account. So it's r d phi. So this h2 is your radius. Cylindrical coordinate, the third direction is z. So the differential length is just dz. Spherical coordinate, most complicated one. In the radial direction, differential length is just dr. R is not angular, so the differential length is not an arc, it's a straight line. Theta, inclination direction. Theta is an angle, so your differential length is an arc. The radius is just r, right? So the Jacobian h2 for spherical coordinate is just r. Phi, the same phi in cylindrical coordinate, as I mentioned repeatedly, the effective radius in spherical coordinate onto the phi direction is a projected radius. So it's r sine theta. So the arc length is r sine theta d phi. Right? So as a test and as an act of confirmation, when you go back home, you don't really need to repeat for the derivation of divergence in Cartesian coordinate, but you might want to start with cylindrical coordinate first because it's easier. It's only having this h2 having the arc. Try to derive on your own based on this definition, and you can just define your structure, your small structure, using a tube or something like that, right? So the center is R0, 0, Z0, right? Somehow, so you have only 3 surfaces. You have one surface going out, one going down, another surface having the R direction. Okay? So try to calculate the divergence and evaluate all the fields going out according to this definition. Right? And you will see whether this generalized expression holds or not. It must hold. What I'm trying to tell you is, in the future, whenever you see this ds, you should have the capability to write out directly the generalized formulation, because when you try to evaluate the first component, you need to have a corresponding surface pointing in the first direction. Okay? A surface pointing in the first direction has its area determined by the differential length in the second and the third directions, and so on. But then you have this delta V differential value, so you have to divide by h1, h2, h3 times the differential increments. Okay? I'm spending a lot of time on this because, to me, your ability to understand and appreciate what I'm teaching would be very important and really allows you to stand out among your classmates. So maybe in the future, if you just memorize like in the past, and if you forget during the examination or any time you forget, you don't know anything. It's like just like you never learned vector analysis. But if your way to learn vector analysis, these mathematical operations, is you start from understanding the basic meaning to the physics, then there's no need for memorizing. Okay, so that's my philosophy. As a student, I never was able to memorize everything, but I was able to appreciate and understand the physical meaning of this equation. Okay? Can you still hear me? All right, so I'm going to close the day with the last slide. Divergence theory. I bet all of you heard of it, but what does it mean? Divergence theory. So this is just divergence. Okay, this is just divergence, the definition of divergence. So you perform the divergence on a vectorial field, you're trying to evaluate all the outward flux on a given small value. That's a definition. So you have this limit, delta V is approaching to 0. So whenever we're trying to perform divergence on the vectorial field A, we're trying to evaluate the flows in the microscopic sense. Okay? So we're trying to evaluate, for example, I have a total of a very big structure, but from the definition of divergence of A, I'm calculating the flow of a very small box inside this structure. So for each point, for each small cube, I know its divergence value. But what about the overall structure? What if I only want to know what is the divergence of the entire structure? I want to know the macroscopic 巨观, okay? Microscopic 微观, macroscopic 巨观. What if I only care about the macroscopic view? I only care about whether this entire structure is acting like a flow source or a sink source. Well, can we move this delta V to the other side? And we change this limitation to integration? Because we can just integrate everything, right? If we want to know the overall evaluation for the big structure, can we add all the results from each small cube together? Of course, yes. Of course you can do that. And that's what this integration means. For each small cube, you know its divergence value. Then we can add all the results from each small cube together to synthesize the result for the entire structure. So that's the meaning of divergence theory. It's just a way of rewriting the definition of divergence. But it's more than that. Okay, it's actually really more than that. So take a good look at this equation again. And tell me, what do you see? We still have 7 minutes. So this is the point I really want your feedback. How many students online? Only 9. So maybe in the future we don't need to have the live streaming. Yeah, it's according to my imagination. But it's already good. I'm giving you some applause. You maintained for 3 weeks. It's already breaking my anticipation. I assumed there will be no one starting from the 2nd week. But I know this is not because of my bad teaching, but this is because the Center of Teaching and Learning Development, they're doing an excellent job in editing the video clips. So I also took a look of the live streaming recording and the edited version. I like the edited version as well. So I don't blame you guys, all right? Take a good look at divergence theory. What does it imply? Over to the right, the idea is each cube, I know its divergence, right? I know the divergence for each cube. And then somehow, to synthesize or recover the entire structure, I'm doing the integration for all the cubes. Okay? So I'm integrating over the entire volume. For each cube, I calculate its divergence, and I integrate everything. So what type of integration is it on the right-hand side? I have to integrate over the entire value of the big structure. So this is volume integration, 体积分 the work is like at least three-dimensional, right? Three-dimensional, x, y, z is a volume integration. But take a look at the left-hand side of the equality sign. Divergence theorem is telling you you can be lazy. If you perform the direct volume integration, it takes a lot of work. If you want to do it, fine, go ahead. But smart students can get the same result just by performing closed surface integration. Surface integration ideally is two-dimensional, right? Reduce is one dimension. So this is telling you you can get the same result from both approaches. But when one student is calculating very hard divergence, performing divergence for each cube and adding all the cubes together, a smart student can get the same result maybe in 1 minute or 30 seconds because he understood what divergence theory tells you. The same result can be derived just by performing the closed surface integration of the vector itself on the outer surface of your big structure. Think about it. For you to calculate divergence of A, you need to know A initially, right? So you calculated its divergence, and you perform a three-dimensional volume integration. It takes time. But the same result can be acquired. You know A already. Once you know the structure, you know its surface. You directly perform the closed surface integration. You arrive at the same thing. So that's the real physical meaning of divergence theory. These two are equal, so you can easily and quickly derive at the same result only by performing surface integration. So you reduce your integration dimension from three-dimensional to two-dimensional. Why is that valid? Why is that valid? We need to come back to the definition. For example, I have a big structure, right? On the right-hand side, I need to calculate the divergence, the outward flow. For each cube, I have 6 surfaces. But for example, I'm taking the front side and the back side. Okay, for example. When I evaluate the outward flux for this cube, by definition, the surface directions needs to go out. Okay? But what happens when I have the second cube? When I have the adjacent second cube, which surface is the same? That surface, right? But in this case, when I evaluate the outward flux for the second guy, this surface needs to take on a direction reverse to that, right? So this is by definition. So that actually tells you whenever you have the same surface, they're canceled out. Because due to the direction outward, for this guy, this surface is taking the green one, going into the blackboard. But for this one, although it's the same surface, but due to the definition has to go out, it takes on the yellow sign. And these two just cancel this out. So let's come back to the PowerPoint. So eventually, no matter how big your structure is, and no matter how many small cubes you have inside it, the common 共用, the common surfaces would cancel out and leaving you only the outer surface. That's the physical meaning to this. No matter how hard you try to calculate, the inner flows all cancel out due to the adjacent commons. Okay? Leaving only the outmost surface not being cancelled out. So you only have to evaluate how much of your vector field is flowing out at the outer surface. The result will be the same as you calculate the divergence of A in making volume integration. This theorem will be most helpful for us to learn about electric field. So you must understand it and appreciate it. Right? So next Monday, we're coming back to curl. You hate curl the most. So do I. But next Monday, we are going to close vector calculus and we're moving on to officially into electric field. So see you next Monday.